learn about dielectric waveguides. So we started learning a nanoparticle and waveguide, and then we're gonna do photonic crystals and so on. So we are basically making our dimensions increase, like a point and the line and the sheet and so on. So optical waveguide. Optical waveguide is a physical structure that guides electromagnetic wave. It's like a pipe, water pipe. Water pipe guides water flowing into it, right? Flowing through it. And optical waveguide is doing the same thing. Like if you launch a electromagnetic wave, optical waveguides guides electromagnetic wave, like in this video, okay? So in this lecture, we want to learn about a few different types of optical waveguide and also try to solve their properties using a simple electromagnetic theory. First thing we want to learn is perfect electric conductor waveguide, because this is the easiest, okay? Now, here we define a few things. We want to make our waveguide into 3 slabs. This is infinite flat material. Here, PEC is perfect electric conductor, which means its conductivity is infinity, okay? So if the conductivity is infinity, the electric field in the steady state, the electric field inside it must be 0. Okay, inside the material must be 0. That's what a perfect electric conductor. And the material in the middle is dielectric with index n. And here we ignore the loss of a material. So this is just a square root of epsilon, assumed to be real. And in terms of the easiest way to understand the wave propagation inside this waveguide is that you have a propagating wave, like propagating plane wave, reflecting back and forth by these 2 surfaces. If you have this type of a picture, then your k vector of the wave can be decomposed into 2 directions. One is parallel to the propagation, k parallel, and then the other is called is perpendicular to the propagation, which is k perpendicular. So parallel component is also called as a propagation constant. So people sometimes write it as a beta, okay, or k parallel, or k sine theta, if you define this theta as this angle as a theta. Okay, so now let's see how we solve. Right. So now, when like what we call waveguide mode is that this mode is basically a transverse field pattern, like this type of a field pattern, whose amplitude and polarization profile remain constant along the propagation direction. So what that means is that like if you translate this into a equation, it's like this. You have x and y direction, which is perpendicular to the propagation direction. So EXY and HXY remains the same along the propagation, and only does and then they propagate with the same beta, or the propagation constant. So if you draw the variation of the field along the z direction, they're just doing oscillating with 1 over 2 pi over beta period, right? So that's what's happening along the propagation direction, and perpendicular to the propagation direction, their transverse field profile remains the same. So that's basically what we called as an eigenmode of the waveguide, so that what defines the eigenmode of the waveguide is beta, right? So once the beta is determined, then you know, the transverse field profile is kind of fixed. So now let's actually try to solve it. So PEC waveguide, we define this axis as z, the propagation direction, this axis is x, and here of course is y. And then here is x equals a, and this x equals minus a. So the thickness of the slab is 2a. And again, the propagation constant, the k vector along z direction is set to beta. And then what we want to solve is E and H along x direction, depending on beta, right? And then we also want to know what type of beta values are allowed. Like, can beta have any value? I mean, what we know is that k parallel, which is k sine theta, if this was a sine theta, it's beta, right? But if you just looking at this explanation, then it seems like theta can have any value, right, between 0 to 90 degrees, so that beta can be any value smaller than k, right? But in reality, that's not the case. We have only a finite number of betas allowed, and you'll see why by taking this lecture. So going back to electromagnetic wave equation, okay? Electromagnetic wave equation is composed of Laplacian and second order derivative along time direction. And because we are assuming e to the minus I omega t time dependence everywhere, right? This is a time harmonic. We are only interested in time harmonic fields. So square root this becomes minus omega squared, right? Taking one time derivative gives you minus I omega e to the I omega t. And then if you do it one time again, one time more, then you get minus omega squared e to the I omega t. So second order time derivative becomes minus omega squared. Okay. So if you do it, and if you look at first look at the left side. Left side is, of course, it's just Laplacian. And then because along y direction, everything is symmetric, so there's no variation. We basically ignore the y directional symmetry. So E is only depends on x and z, right? And then so we have x dependence. And another thing is because we are solving for the wave propagating along z direction with the dependence of e to the I beta z. So second order derivative along z becomes minus beta squared. So xx, the right hand side becomes like that. Left hand side, as I said, second order derivative of time becomes minus omega squared. So it's like that. So this equation can be simplified like this. Very easy, right? And now, if you solve this equation for x, then here everything is constant. It's not depends on x. And then here you only have second order derivative. In this case, solution is obvious. Solution is just the cosine and sine. This is the general solution. With k, with kappa is basically square root of epsilon omega squared divided by c squared minus beta squared, right? So this is general solution. So what we need to do is to determine the coefficient or and k. So now we apply the boundary condition. So what's the boundary condition? In this case, the boundary condition is that PEC, in the PEC, electric field must be 0, right? And then, yeah, so the electric field must be 0. That's the condition. And then if you apply that condition into like two choices of equations. So like, let's say in the core, as I said, we have this general solution. And then in the cladding, electric field must be 0, right? And if we apply that condition, and here also, once you know the electric field, you can always obtain a magnetic field without any problem by using this Maxwell's equation. So if you apply the boundary condition here, electric field becomes 0 at the boundary, then you obtain for the symmetric mode, kappa A must be half integer multiple of pi, and then asymmetric case, like in this solution, sine kappa A, kappa A must be the integer multiple of pi. Okay, and then you can visually see why this is the case. Like, let's say first look at the cosine kappa x solution, and cosine kappa x solution should look like this, right? And in this case, because of the boundary condition, electric field must be 0 here and there. And that gives you only a finite options to choose your kappa here, kappa. So what are the possible options? Possible options are, of course, this is the first possible option. And second possible option is this, right? And third possible option is this, and so on, right? So there are only a few allowed kappas for the symmetric wave. And similarly, for anti-symmetric wave, like if the solution is sine kx, now it has this type of a form. And then if you apply boundary conditions, then this is the first allowed. And second allowed is what? Second allowed is so something like this, right? And so on. So from this, what we know is that kappa must satisfy certain condition in order to satisfy the boundary conditions, right? And you remember kappa and beta are related. So if the kappa has only a few choices, then beta also have only few choices. So that limits the number of allowed propagation mode in the PEC waveguide. So if you draw the dispersion relation, so dispersion relation for M's mode here, beta again is epsilon omega squared by c squared minus kappa squared. And then kappa have this relation, right? Only a half integer multiples are allowed. So if you draw omega as a function of beta and kappa, it looks like this. So if you draw omega as a function of beta. So beta again is the propagation constant, k vector along propagation direction. Omega is about the frequency. So if you draw it for different m's, for different choices of kappa, for m, when m equals 1, it has this form, m equals 2 has this form, 3 this form. So you can draw the dispersion relation of each mode like this. Okay, and then we can use this number 1, 2, 3, like m equals 1, 2, 3 as a mode identifying number, like m, like TE1, TE2, TE3, like these are all different numbers. And then what you can see here is the all these modes has cutoff. So what I mean by cutoff is that let's look at TE1 mode. If you look at TE1 mode exists only above this frequency. Below this frequency, there's nothing, right? And TE2 mode, it's only allowed above this frequency, but below this, there's no TE2 mode, right? So that means TE1, TE2, TE3, and all the other modes have cutoff frequency. And then that cutoff frequency, of course, is determined by this equation. So we know that beta, the propagation constant, must be real, right? So that beta squared must be positive. So omega must be larger than ck divided by square root of an epsilon. So as kappa increases, like kappa, which is like this, as kappa increases, there is a omega constraint is applied. So your mode is available only above certain frequency, right? So that's the cutoff frequency for m's mode. And what I would like to say here, what I would like to give here is a simple, how can I say, simple explanation of why this is happening. And so, as I said, we have cutoff frequency, omega m, for different mode. And then we can interpret this in this as a ray optic manner. So let's say, yeah. So here theta. So if we interpret this in a ray optic manner, and then we can obtain theta from kappa and the index of a material. So in this material, the k vector, the total k vector must be nk0. That's what we know. And then kappa is the out of plane wave vector. So if you take the ratio and then take the cosine, then you can obtain arc cosine, you can obtain the theta, right? And then and then you can realize that here, so at the cutoff frequency, the omega m is equal to this value, which means theta becomes 0, right? So omega m becomes this value. When omega m becomes this value, then what's inside becomes 1. So arc cosine becomes 0. So which means the situation is like the wave is impinging on the interface in a 90-degree angle in a normal instance, so that the wave cannot propagate, but just going back and forth over and over. So that's, and because of that, above this frequency, it's not possible. The propagation is not possible. So if you look at what's happening at higher frequencies, so at higher frequencies, omega, so omega is large. That means the total value is smaller than 1, right? So that we have finite theta, non-zero theta, which can be interpreted that, okay, you have wave propagating, like reflecting back and forth with some angle so that the wave can still propagate, right? But as your omega becomes smaller and smaller, lower and lower, then your K vector becomes shorter and shorter so that the incidence angle theta becomes smaller and smaller. So it becomes more and more less propagating. And then when theta becomes 0 or omega becomes omega m, you reach the cutoff frequency. So it's just going back and forth. Okay, so this is a ray optic interpretation of the thing. And another thing that I'd like to address is that, so now you have dispersion relation. So from this, you know the group velocity of the mode, not only the phase velocity, but also the group velocity of the mode. And then, as I said, group velocity of the mode, you can obtain d omega dk, right? In this case, k is beta. So group velocity is d omega d beta. And you can see when things are hitting the cutoff, the group velocity becomes 0, right? Which means at the cutoff, the wave cannot propagate. Like it just doesn't convey any group movement, whereas its phase velocity is still non-zero at the moment. Okay, so I guess I will stop here today.